There are four common types of random sampling. We'll always use simple random sampling in this class, but stratified sampling is usually more precise and cluster sampling tends to be cheaper and more convenient. So it's worth it to explain how these various forms of sampling work. With simple random sampling, you want to get every element of the population to have the same probability of winding up in the sample. You have to get a list of the whole population and randomly choose some. And that's easier said than done. For example, if you wanted to study income in some area and you get a list of residences in that area and randomly choose some of these houses, you would be leaving out homeless people and maybe people that have multiple residences or something. So there are some people that would be more likely than others to wind up in your sample. And random samples always have issues of those sorts, and I don't think it's possible in a lot of cases to get a truly random sample. But everything we do going forward is built on top of this foundation of randomness. So it is very important to try to get the sampling right. Sampling is done either with replacement or without replacement. Think of sampling marbles from a bag. Maybe you have a bag of 100 marbles, 50 red and 50 blue. You shake up the bag and draw one out. It's red. Now, if you put that marble aside and draw another one, you're sampling without replacement. On the first round, you had a 50 out of 100 chance of getting a red marble. But on the second draw, there are only 99 marbles left, and only 49 of them are red. So your probability of drawing a red on the second draw will be 49 out of 99. So it's slightly different. Um, Now, sampling with replacement means that you put the sampled elements back into the pool. So now if you draw a red marble, you put it back and then draw again. The probability of getting the red marble was 50 of 100 on the first round, and because you just put it back, it's going to be 50 out of 100 on the second round. So there's a little bit of a different probability dynamic when you sample with replacement versus without. Here's an example to demonstrate the difference between simple random sampling and stratified sampling. We have this farm, and on this farm are 12 cows, 48 sheep, and 240 chickens. I want to find the average weight, that is the mean weight of animals on this farm. So the 300 animals are my population. I'm going to sample from this population. To find the population weight, I'd take a census. I'd weigh all 300 animals, add up the weights, and divide by 300. Doing that gives a population mean of 93.66 pounds. And remember, the population mean is a parameter, not a statistic. But usually it's not feasible to take a census, so we have to estimate the parameter with a statistic. We'll take a sample, find the sample mean, and use that as an estimate of the population mean. The question is, how good of an estimate do we get? I take a simple random sample of 25 animals. Now, the population proportion was 12 cows, 48 sheep, 240 chickens. And if you divide each of these numbers by 12, you get 1, 4, 20. So a representative sample of 25 animals would be 1 cow, 4 sheep, and 20 chickens. If I get a sample like that, the sample mean weight will probably be close to the population mean weight. But there are a lot of ways I could randomly draw 25 animals. I could easily wind up with too many cows, which would drag the average way up. I might also get a sample that's all chickens, and the estimate would be way too low. With stratified sampling, we can sample using the same proportions as the population. What you do with stratified sampling is you group all the similar items together. So here I'm grouping the animals by species. Then you take random samples from the groups in proportion to the population. In this case, I will randomly draw 1 cow out of 12. I'll randomly draw 4 sheep out of the 48 and 20 chickens out of the 240. This will guarantee me a sample that's representative of the population with regard to these groups. I took 100 simple random samples and 100 stratified random samples, and I'll show you a little bit about this in today's code. Here's the graph. The x-axis is the trial number. There were 100 trials, so it goes from 1 to 100. The y-axis is the sample mean. The dotted line is the population mean. Notice that all of the stratified sample means hover around the population mean. The simple random sample means are also pretty evenly dispersed above and below the population mean, but there's a much greater range of values. Some of these really low ones look like they're around 10, and the highest average appears to be close to 300. This graph is showing us that as an estimate for the population mean, the stratified sample mean has lower variance. It is the more precise estimator. We can also do cluster sampling. With cluster sampling, you want each of your clusters to resemble the population as much as possible. You randomly draw some clusters and measure everything in the cluster. Here, I made 12 clusters of 25 animals. If I want a sample of 25 animals, I can randomly draw one of the clusters and weigh every animal in it. And you can see how this procedure is going to work best if the cluster looks like the population. It would be off by a lot if you have clusters that are all chickens or contain multiple cows or what have you. If I wanted 50 animals, I'd randomly draw 2 of these clusters. With regular cluster sampling, you only sample the clusters. You have to measure everything in the cluster. Multi-stage sampling refers to cluster sampling where you sample within the clusters. In this case, I could randomly select 5 clusters and then randomly select 5 animals from each cluster. That would be two-stage sampling because I sampled in 2 stages. The difference between strata and clusters is that strata should be groups of similar things, clusters should be groups of diverse things. Stratified sampling is more precise than simple random sampling. Cluster sampling is less precise than simple random sampling. Cluster sampling is usually done because it's cheaper and easier than simple random sampling. Analyzing the data from both of these methods is more complicated than it is with a simple random sample, because you have to split up the variability into components. One source of variance comes from the difference between the groups, and one is from the difference within the groups. And they have to be handled separately because of the sampling of the groups. To see what I mean, let's look at the group cows and the group chickens. Some of the variation that we see in the data comes from the fact that cows weigh different from chickens. And this is the between group variability. On the other hand, some of the variation we see comes from the fact that individual cows have different weights and from the fact that individual chickens have different weights. And that's the within group variability. In this example, most of the variance we see in the animal's weights is coming from the between group variability. We want our sample to be representative of the population, but we never know whether it is or not. Almost everything we do in this class involves comparing the behavior of our data to the behavior of a random sample. Random sampling is crucial to the analyses that we will see.